Excellent. So, levitation, from hovercrafts to holograms. I just want to start by saying that I hope this talk will be very uplifting. I think it's good to break the ice with a terrible joke, sets the bar for the tone of humour that you're going to get throughout this talk. You may leave now, I won't be offended. So what is levitation? We've all got an idea. We've seen it in media, like magic spells or something, but we're all nerds here. We like a proper definition. So, from the Merriam-Webster dictionary, to rise or float in seeming defiance of gravitation. All right, so far so good. Magic spells are in. But does flying count? Because planes can float in the air, but no one says planes levitate. Maybe that's because you don't see planes still in the air. They're always moving, so perhaps that's the key difference. And in that case, does a helicopter count? I found another definition, this time from Wikipedia. Levitation excludes floating at the surface of a liquid because the liquid provides direct mechanical support. So I guess boats don't levitate, but maybe we didn't think that. But it goes on. Levitation excludes hovering flight by insects, hummingbirds, helicopters, rockets, and balloons because the object provides its own counter-gravity force. So helicopters are unfortunately definitively out, and probably hovercraft for the same reason. So sorry for the clickbait title, but I promise you there will be more levitating methods of transport later in the talk. So levitation seems to be something that happens to something rather than something an object does that it provides its own power to do. So that's a good start. We've got an idea of what levitation is and some things that it isn't. So far, all of the things I've mentioned have one thing in common, and that's air, which actually, spoiler alert, is a bit weird because most of the methods of levitation we're going to talk about today don't involve air and can happen whether or not it's there. But there is one kind of levitation for which air is completely essential, just in a very different way to a plane. So we're going to start with acoustic levitation. For each of the methods of levitation that I'm covering today, I'm going to tell you a bit about how they work, why they're useful, and what's the coolest or weirdest thing that we've levitated. So acoustic levitation, as you might expect, uses sound to make stuff float. We know that sound is just wiggly air. And you can think of a sound wave looking like this. It's got amplitude, and that's the height of those peaks, and it has phase, which is where those peaks and troughs happen. According to the principle of superposition, waves can add up. So if I have two waves looking like this, if they're moving at the same time, there'll be parts where they're moving together and they have that big displacement, or parts where they cancel each other out. So you can see the waves in blue and green are the two waves that I'm adding up to get that wave in red. And the phase of those waves, where they have those peaks and troughs, in this case, it makes what we call a standing wave. So some parts of the air are moving maximally, and some parts of the air are completely still. So now imagine getting two speakers playing those waves at each other. Congratulations, you've just built your first levitator. Wow! If you place a polystyrene ball into the column of air, it'll be trapped in the low pressure zones between areas of high pressure, and it'll be suspended. Now, theoretically, you can use any size wave, but most often we use ultrasound. So that's a frequency that's above the range that humans can hear. 40 kilohertz is common, perhaps because audible sound would be really annoying. And transmission in air drops off with frequency. So using higher frequencies, the wave doesn't travel as far, so it's a good balance. It's also the frequency that a lot of car reverse parking sensors work at, so it's easy to get parts. You might have already known that you can use sound to break glass, but now you know that you can use sound, enough reverse car parking sensors to levitate objects. So that example setup just had two speakers. If we add more speakers, we add more power, and we can offset the waves that are being produced by each of the the speakers so that their peaks and troughs happen in very specific places and create that interference exactly where we want it. And if we keep scaling this up and adding maths, we get a much bigger levitator that can handle multiple particles. What it actually creates is a sound hologram, because you're producing a 3D sound field. So in the same way that a hologram, an optical hologram, is producing a 3D image from a 2D medium, we've got a 2D array of speakers producing a 3D field of sound. And this lets us move these particles really fast and with great precision, so we can make 3D shapes through the persistence of vision. That's the same way that all the pictures in a flick book, if you play them fast enough, they look like a video. So I hope this video works. You can see we've got one little polystyrene ball being levitated. It's moving really, really fast, and at a certain point, instead of seeing one individual particle, you see kind of a solid circle. And I think in a minute, it's also going to show an example with multiple particles creating a little butterfly. Wow. But there's lots of other uses. If you want to know how stuff crystallizes, that's actually a really difficult thing to study, because any container that you have the stuff in can have an effect on that process. So if you do it in midair, that's problem solved. And this might end up giving us better chocolate, because cocoa butter crystallizes on the surface of chocolate as it cools. And if we can understand that process better, we might be able to make designer chocolate. Another thing it's useful for is levitating bugs. A relevant quote I got from a research paper was, using this process ensures the specimen is not physically damaged, and all parts of the specimen can be viewed as no pin is blocking the view. It also ensures insects too small to be pinned can be imaged, so we can take really great 360 pictures of tiny bugs and learn more about them. But one big drawback of this type of levitation that we've seen so far is that all that stuff is really small. So I'm going to ask a question that I will ask of all the levitation methods that we talk about today. Could it levitate a human? Since the trap that the particles are suspended in is created by the islands of low pressure between high pressure parts of the wave, the spacing of those areas is determined by the wavelength of the sound. To levitate larger objects, you just need a higher wavelength, therefore a lower frequency sound. Fine. So we just use lower sounds. But there's another problem. We need a lot of force to lift a human, so the sound is going to be really loud. You've probably experienced being able to feel sound before, maybe even in null sector last night, and that was quite loud. Nobody levitated, so it's going to have to be a lot louder than that. And all that energy, moving all that air, is going to generate heat as well. So basically, if we tried to levitate a human this way, I'm not sure if it would deafen you or boil you first. So I'm going to go with probably not, sadly. So to sum it up for acoustic levitation, the pros, it's precise, it's material agnostic, which means that it doesn't matter what kind of material you're using, it just matters the size of the material. The cons, it can only levitate small things, and it might upset your cat or dog because they can hear sounds of a much higher frequency than we can. The strangest or coolest thing that we've levitated, I have a picture here of a tiny fish. It's a little bit pixelated, but I had to include it. And also a video of a very confused ant. In the rest of the video, they go on to say that the ant was unharmed, if a little confused. And then, can it levitate a human? Sadly, probably not. So what kind of levitation can we use if we want to lift bigger stuff? What about magnetic levitation? If you've ever played around holding magnetic poles of magnets, fridge magnets together with their like poles facing, then you've experienced magnetic levitation. Except you haven't, because of this guy and his annoying theorem, Earnshaw's theorem. Way back in 1839, he used some clever maths to prove that for any force that varies as the inverse square of distance, point charges cannot create a stable equilibrium. That sounds complicated, but all it means is that if I have a bunch of permanent magnets, even though there's a repulsive force between the like poles, which is all I really need to counter gravity, there's no way for me to arrange them where that would be stable. And by stability, we mean that whatever force we're using to levitate, we want the distribution of that force to be such that if I disturb my levitating object, it wants to get pushed back to where I put it, and it's not going to fly off into the distance somewhere. And one way of picturing the difference between stable and unstable equilibrium conditions is thinking about a ball and a bowl. If I turn the bowl upside down, I can perch my ball at the top of the bowl. But if I so much as breathe too near this, it's going to roll down and fly off into the ether. But on the other hand, if I turned the bowl the other way up, arguably the correct way up, and I put my particle at the bottom, now what's going to happen if I disturb it? It will roll back down the sides of the bowl and remain where I left it. Earnshaw's theorem basically just says magnets are more like the first bowl than the second one. So is that it for magnetic levitation then? Is it impossible? Enter the levitron. It was invented by a guy called Roy Harrigan, and I found this beautiful article from Popular Science in 2004 that has this line. I simply have to quote, Harrigan had one distinct advantage over all those scientists who had tried and failed to levitate magnets before him. Complete ignorance of Earnshaw's theorem. Having no idea that it couldn't be done, he stumbled upon the fact that it actually can. This is a desk toy where a spinning top can levitate above a fixed magnetic base. It works because the angular momentum of the spinning magnet prevents it from flipping over and being attracted to the magnet in the base. And there's also some effects with the gyroscopic movement of the top precessing around the magnetic field lines. It's not immediately obvious how it works, and this might not be the only time I say this in this talk, but trust me, the maths works out. But it will stop spinning eventually because air resistance is going to cause it to slow down, and when it slows down, the angular momentum is not enough to counter that force anymore. It tips over and touches the base. But an interesting aside, what happens in a vacuum when you don't have any air to slow it down? There's a quote from the original pamphlet that came with the toy that says, in some vacuum experiments, the top falls after about 30 minutes. Why it does so is not clear. So if you have any ideas, come and see me in the Q&A tent afterwards. And then if you want to try this at home, I have an example of an experiment that you can do with a rotary tool and two small magnets. I personally was about to say that this is a great way to win bar bets, saying I bet I can levitate that magnet right there in front of you, but I mean, I don't know if you bring your rotary tool to the pub. I think in this crowd, there's probably a larger percentage of people for whom the answer is yes. And you might have seen those desk toys that you get, or little planters where they're levitating. They look pretty stable, so how are we getting around Earnshaw's theorem there? Well, Earnshaw's theorem holds for a fixed arrangement of magnets. But who says we have to have a fixed arrangement of magnets? What if we could move the magnet underneath to counter any perturbation? And better yet, what if we use electromagnets? So here at Electromagnetic Field, we probably already know that electricity and magnetism are best mates. They're like that annoying couple that go everywhere together. And yes, my husband is in the audience. And whenever an electrical current flows through a wire, it causes a magnetic field. And similarly, when a magnet is moved near a conductive object, it induces a current to flow in that nearby conductive material. So take a coil of wire, pass some current through it, you've made an electromagnet. You can turn it on and off, and you can adjust the field strength by changing the amount of current that you're passing through the wire. So that's how you cheat Earnshaw's theorem. A static field can't give us stable levitation, but a changing one can by using electromagnets to adjust the strength of the field and nudge the levitating object back towards the center all the time. So let's sum up for magnetic levitation. The pros: readily available, all you need is a magnet, and it's got a pretty strong force. Cons: only works with stuff that's magnetic. And that leads me on to the next point. What's the coolest or weirdest thing that we've levitated with this? I'm going to have to say a funny-shaped magnet, because those desk toys are really cool, and they might count, but really it's just something sat on top of an object that's levitating, so I'm not counting them. And I was about to say, I don't make the rules, but this is my talk, and I do. So I'm sorry, it doesn't count. And then, could it levitate a human? Well, I'm sorry to have to be the one to tell you, but you're not magnetic, so unfortunately, no. Since there's a link between magnets and electricity, perhaps the next kind of levitation we should look at would be superconducting levitation. So a weird thing happens to some materials when you get them really cold. They become superconductors, which means that an electrical current can flow through them with virtually no resistance. And having already seen that there's a link between electricity and magnetism, I think you can guess where we're going with this. A magnet near the superconductor can induce a current, and usually the material would have a resistance to this electric current, so the magnetic field that that current produced would be limited. Not so much in a superconductor, and it creates a perfectly opposing magnetic field. Now that's quite a crude description of something that has a lot of other quantum mechanical aspects and effects. Again, trust me, the math works out. And that's not really in the scope of this talk, but if you're interested to know more, you can look up the Meissner effect. One use of this method of levitation you might have heard of is maglev trains. Since they essentially hover over the track, they don't have friction between the wheels and the guide rails the same way that normal trains do, so it's much easier without having to counteract that drag force to reach really high speeds. The first commercially operated maglev train was in Shanghai in 2004, but I believe the current world record holder for the fastest maglev train is Japan. Their maglev train has superconducting magnets on board and then two coils, sets of coils in the guideway, and by manipulating the current in those coils, they can propel the train, and it hovers about 100 mil above those tracks. And their world speed record for a crude train is a crazy 373 miles per hour. Another weird advantage, maglev trains might not be able to derail in the same way that normal trains can. The further a maglev train gets away from its central point in the guide rail, the stronger the magnetic force pushing it back to the center. And it's also useful for whatever this is. I found this picture with no context on a blog post by Nidec Corporation, which is a Japanese manufacturer of motors. This is the only reference I can find to it anywhere on the internet, and I thought it was just so silly I had to share it. So enjoy the levitating fish. The second one of the talk. So to sum up for superconducting levitation, pros, we can levitate really big stuff like trains. And it's pretty energy efficient once it's up and running, but you do have to cool things down to ridiculously cold temperatures, which is a bit of a con. What is the coolest or weirdest thing that we've levitated? Again, I would be tempted to say maglev, but like the last example, it's really other stuff resting on top of an object that's levitating, so it kind of doesn't count. Could it lift a human? Still no, you're still not magnetic. And also, you probably wouldn't like being at minus 200 degrees. So what other options do we have for non-magnetic materials? What about diamagnetic levitation? This is kind of a halfway house. When I said earlier that you weren't magnetic, I wasn't being completely honest. You might be diamagnetic. Lots of materials that aren't fully magnetic are diamagnetic, meaning that they exert and feel a slight repulsion in a strong magnetic field. This is the result of electrons in the material changing their orbits, which creates a tiny circulating charge, and we know that currents create magnetism. The difference to a normal magnet is that this is only a repulsive force, there's no attractive element, and it disappears when there isn't a magnetic field around to create the effect. But repulsion is all we need to counter gravity and make levitation happen. There's not a lot more of inner working to this one, it's just magnets repelling each other, but some of the uses have been interesting. And one of my favorites is levitating live fruit flies. So we want to study the effects that microgravity has on different organisms to tell us things about how space affects living things. But shooting fruit flies into space is expensive and time-consuming, so if we can simulate a microgravity environment on Earth, it's a lot easier to do the research. They've actually done a similar experiment in space, however. Interesting side note again, Quote from the research paper, "The flies on the ground did not experience the conditions of the shuttle launch. Indeed, subsequent experiments showed that the behavior of the flies on the ISS was sensitive to launch procedures." So flies are sensitive to space launch. That's an interesting fact we now share. So, if we can levitate flies, the all-important question is, can we levitate a human? My answer is going to be maybe, because we've levitated a frog. And broadly speaking, we're not too dissimilar from frogs. We have a comparable density and diamagneticness, so the strength of the magnet that we needed to do it might be kind of similar. However, it would need to be physically larger in size because most of us are a bit longer than a frog, and it was pretty hard to make the first magnet that we used to levitate the frog, considering it was about 1,000 to 10,000 times stronger than a fridge magnet, or about 10 Tesla if you like weird units like I do. But if we could make that magnet, unlike some other kinds of levitation, if we used that to levitate you, you'd probably be fine. By all accounts, the frog was unharmed, and joking aside, you might have experienced a really big magnetic field before, because they're used in MRI scanners, and they're perfectly safe. We use them all the time. So summing up for diamagnetic levitation, pros, most materials can do it. For us, I think it's the water in our bodies that's the component that has the strongest diamagnetic So that's the same reason that the frog and us can both levitate. So lots and lots of materials are capable of doing it. And all you need is a really big magnet. But that's kind of also the con. You need a really big magnet. And it's not as precision controllable as some of the other methods that we've talked about. The weirdest or coolest thing that we've levitated, it's got to be the frog. Look at him. And could it levitate a human? We're going to go with maybe. So we talked about magnets on their own and about magnetism and electricity being best friends, but we haven't talked about electricity on its own. Unsurprisingly, our old friend Earnshaw has something to say about this as well. So we've got positive and negative charges. They're not unlike the north and south poles that we have in magnets. So we already know there's no stable configuration of individual charges that will give us levitation, just like with magnets. But just like in the previous example, it doesn't count if you vary the charges over time. So pop a charged object between two plates and control the field between them, and bingo, you've got levitation. We use this often for studying molten materials and other materials without having to put them in a crucible which could contaminate your sample. And it's been proposed as a way to propel craft on other celestial bodies where the surface has a charge present. I don't have a ton to say about this kind of levitation because although it's used in a lot of really interesting and useful material science research, looking at the properties of materials and how we can build different metamaterials, I think the researchers aren't doing enough goofing off and levitating frogs and flies. Boo. So summing up, electrostatic levitation, pros, it's possible with limited equipment. You just need your electric charge. But it does only work for charged objects, and we need a really high voltage to do it. Coolest or weirdest thing that we've levitated, did you know there are fountains of dust on the moon? So the dust gets charged by ultraviolet and X-rays from the sun, which knock electrons out of the atoms and molecules in the dust, and that causes positive charge to accumulate, and these tiny 1 micron little tiny particles of lunar dust are repelled up to 1 kilometer into, well, I was going to say into the air, but into space. And this was observed by the Apollo astronauts who saw a haze on the moon's horizon that was quite difficult to explain considering the moon doesn't really have much of an atmosphere. And those are some pictures, actually, of the moon haze that you can see. Could it levitate a human? I'm going to say no. You'd need such a high voltage that you're likely to turn into a conductor for that high voltage, much to your detriment at that point. So another kind of levitation that might have something to do with space is optical levitation. So light is, well, very light. Photons of light are massless, but they do have momentum, some of which they impart on any object that they hit as they scatter and go off in a different direction. And physics tells us that momentum is conserved, so if the photon's momentum, that's its speed and direction, changes, so must the momentum of the object that it interacts with. The force is admittedly tiny, but the trick is to use a lot of photons, and if they're all pointed towards the center of the object, then the net result is the object is trapped where it is. And you can do it in a vacuum, unlike acoustic levitation, for example. One vacuum where this might be relevant is space. We've been using solar sails to propel craft for a long time now, and they work just like the sails on a boat, but instead of having air particles hitting them and propelling them, we're using photons of light to do the work. And one cool thing we've done with optical levitation is to make the fastest spinning object we've ever made. A quote from the research paper: with a circularly polarized laser, we drove a nano dumbbell to rotate beyond 1 gigahertz, which is the fastest man-made rotor in the world. That's 60 billion turns a minute, so it really is fast. And also, just a side note, I don't know if the fastest woman-made rotor in the world is any faster, but we will leave that as an exercise for the readers. What are the pros and cons of optical levitation? So, pros, works on some extremely tiny scales because photons are very small. Cons, you need some seriously precision equipment and optics to make it work. And weirdest or coolest thing that we've levitated, diamond dust. And that's not just because it's really pretty, it's because nanoscale defects inside diamonds can be used as magnetic sensors. And researchers have this idea that if they grow neurons on top of this diamond dust, they could create a kind of diamond sensor, so they could measure the magnetic field created by the neurons. And that could really open up some areas of research in neuroscience that would be really, really interesting. Could it levitate a human? I'm going to say no. Lasers already burn stuff, so you'd probably be blind and on fire before you took off. And the final one that I'm going to talk about is good old air levitation. In a way, this is the messy cousin of acoustic levitation. It mostly involves using a jet of gas to suspend something. You don't have as much precision control as with, say, acoustic levitation, but it lets you lift larger objects more easily. Part of what's key to this is the Coanda effect, which is the tendency of a fluid jet to stick to nearby curved surfaces. And we can use this to our advantage to make high and low pressure air zones where we want them to produce airflow that generates lift. It's kind of a crude approach in a way, but it lets us study how materials turn into glass, for example, which could give us better lasers, fiber optics, useful stuff like that. For example, refractory oxides are materials that survive extremely high temperatures, which makes them really useful for building things like spaceships. But studying them at high temperature is really difficult because any container you put them in or surface you put them on is likely to melt before you get up to the temperature that you want to study them at. So you blast some air, you can suspend your sample on that airstream while you heat it, and you don't need any sensitive equipment nearby. But besides that useful stuff, this method has given us air hockey, which I think we can all agree is vital. The limit really is your imagination with this one. Here's a video of a guy levitating carrots. And he's going to levitate a second carrot in a minute. And I just love, watch out for the little caption that comes up at the bottom of the video as he does the second carrot. Every carrot was successful. So, very quickly summing up air levitation, pros, all you need is air. It's very robust, it works with most materials. The cons, it's not very precise, and it could damage smaller objects or more delicate things. The weirdest or coolest thing we've levitated, I mean, I think all those examples were pretty weird and cool, but also, could it levitate a human? The answer is, it kind of already has. Indoor skydiving is kind of how this works. So my final slide, these are all the kinds of levitation that we have covered today. And what I'd really like to do, just very quickly at the end, is to get a show of hands for each one of these methods to find out which is your favorite method of levitation. So we have acoustic, magnetic, superconducting, diamagnetic, electrostatic, optical, and air. Hands up for acoustic. Okay, strong start. Magnetic. Okay, that looked pretty even. Superconducting. Okay, yeah. It is cool. By definition, it's cool. Diamagnetic? This is quite split. I was expecting there to be like more towards one or the other. Optical? Oh, that's just one vote for optical. And air. What about air? We've got a couple of fans. Excellent. So I've got to tell you now, full disclaimer, the best kind of levitation is acoustic levitation. You were all wrong, apart from the ones that put their hands up first, and that is because acoustic levitation pays my bills. I work for a company that levitates stuff with sound, and we're making cool devices to use in labs and to sort seeds. And I will be at the Q&A tent afterwards if you want to ask me about that. Thank you very much.